Hello again. This is Math 2134 coming to you from the College of DuPage, and the title of this lecture is Solving Certain Differential Equations via Integration. Remember to be an active learner as you watch this video. This aligns with this section in the book, and what we're going to be doing is determining general and particular solutions of differential equations. We're going to learn how to verify that a function is a solution of a differential equation. We're going to learn a technique called separation of variables we'll use to solve differential equations. We'll solve differential equations using the uninhibited growth model, and we'll solve a couple of applied problems using separation of variables. As you'll recall, in Chapter 2 we studied an important equation that was if the derivative with respect to t of p of t is k times p of t, or, more generally writing it, d p dt equal kp without the t, we saw that this had a solution that was p of t is equal to p0, the initial value, and times e to the kt, where p0 is the initial quantity at time t equals 0, and this is called an example of a differential equation. You see it's got a derivative in it and it's got a function. And in fact, this is the broad definition we'll use. A differential equation is an equation. You see there is an equal sign that includes a derivative, and it certainly has a derivative, and has a function as a solution. So this was the solution to this differential equation. In differential equations, p and p of t are also used interchangeably, as are dp dt and p prime of t. And sometimes they'll even say y prime for a derivative. So if y is f of x, then y prime is equal to dy dx equal f prime of f of x. You remember all that from the first part of this course. Now, certain differential equations are solved just by finding the antiderivative. For example, we know dy dx is equal to f of x, or y prime equals f of x. What we can do is basically multiply, or at least it appears we're multiplying, both sides dy by dx, and so we'll have dy is equal to f of x dx. So we integrate both sides. The integral of dy is y, and this is the antiderivative of f of x dx, and that's capital F of x plus c, where the derivative with respect to x of capital F of x is equal to lowercase f of x. Now that's what we've done before. So what happens is that an indefinite integral results in a set of functions. So there could be infinitely many solutions, and these are called the general solution when there is an infinite number of such solutions. Let's let an example be worth 1,000 words then. So we want to find the general solution of y prime is equal to 2x. So we have dy dx is equal to 2x. Writing in this form is useful because then you can think about multiplying both sides by dx. Then you're going to have dy is equal to 2x dx. This is a dummy variable, this is a dummy variable, so we can integrate both sides. When we integrate dy, we just get y. When we integrate 2x, we get x squared plus c. Now you might say, oh, we get a constant over here, Jim, and a constant over here. You do, but we just lump them all together here. And we certainly can always check this by taking the derivative of the answer and seeing if we get 2x, and we do. So that is a solution. And in fact, it's a family of solutions. So for different values of c, you get different curves that are a solution. But if we know a specific function value, this often allows us to find a particular solution. For example, if we know that when x is 1, y is 4, then we can substitute that in to the equation, and we can learn that y is equal to x squared plus 3. The requirement that 1, 4 must be included in the solution is called an initial condition. Often an initial condition is given by y of a equal b, and that is called a particular solution because it goes through a particular point, 1, 4. We can also talk about verifying solutions to a differential equation. So to verify that a function is a solution to the differential equation, what we have to do is find the necessary derivatives and substitute into the equation and show that both sides are the same. For example, whenever we had to show that p of t is equal to p0 e to the kt, we substituted that in. We found that both sides was true, so that was a solution to this differential equation. Let's do another example. This one is y prime is equal to 2xy. So in part A, we're supposed to show that e to the x squared is a solution. Okay, so we take y is equal to e to the x squared, and then we'll take y prime equal to this, and we will substitute. So you see we're going to subtract this from both sides, and so we'll have y prime minus 2x, and again we're letting y equal e to the x squared, and we need to show that that's equal to 0. Well, we take the derivative here, and the derivative of e to the x squared is e to the x squared times 2x by the chain rule, minus, and this is 2x times e to the x squared, so it's 0. So 0 is 0, so it is true. Therefore, y equal e to the x squared is a solution of y prime minus 2xy is equal to 0. In part B, we're being asked to show that a constant times e to the x squared is also a solution where that is any constant. Well, if you put the constant in, what happens is you can divide all the way through by c. Y prime is going to be equal to that, and so the c's will cancel, so you see it's the same kind of thing, and it again is equal to 0. Now this is called the general solution because we included the constant. Now a differential equation may include second or higher order derivatives. Many of the equations of mathematical physics are second order differential equations. So recall the way you get the second derivative is first you take the first derivative and then you take the derivative yet again. There's no one-step process to get there. So let's look at a third example, and we want to show that y equals 4e to the x plus 5e to the 3x is a solution of y double prime minus 4y prime plus 3y is equal to 0. So this is what we're going to show as a solution to that. So first we have to calculate y prime and y double prime. So y prime is going to be 4e to the x plus, and when we take the derivative of this, it's the 5 just sits there, and this is going to be e to the 3x times 3 by the chain rule. And so that's 3 times 5 is 15. So when we take the first derivative, we get this as our derivative. Make sure you're following these calculations. It's good review for the final exam. But then we take the derivative again. So we're taking the derivative of this one. Again, we're going to get 4e to the x plus, but now the 15 just sits there, but the derivative of e to the 3x is e to the 3x times 3. 3 times 15 is 45, and this is what we get. So now we're going to take y double prime, and this for y prime, and we'll substitute it into this equation and see if we get 0. So here we're substituting y double prime minus 4, that's y prime, plus 3, and we substitute what y was, and we try to see, is this equal to 0? Now we start simplifying this side, and so we collect like terms, and we simplify. You should verify all this, but what happens is you got 4e to the x, and then you got minus 16e to the x plus 12e to the x. That gives 0e to the x. And the terms with e to the 3x are 45 minus 60 plus 15. So it's 0, so 0 equals 0. So that's a true statement, so we've confirmed that this is a solution to the differential equation. Now, some differential equations are called separable differential equations. And in a separable differential equation, what you're able to do is do algebra on this expression and get it into this form. So the definition of a separable differential equation is a differential equation that after you do algebra can be written of f of y dy is equal to g of x dx. Notice that the left-hand side is only a function of y, and the right-hand side is only a function of x. We've separated the variables. That means then we can integrate both sides and find a solution. Now, the equation up here, this one, that we started out with is a separable differential equation, because you notice that we can reorganize this by dividing both sides by y and multiplying both sides by dx, so we get 1 over y dy is equal to 2x dx. So you see the left-hand side is just a function of y, and the right-hand side is just a function of x. So we can integrate both sides. Here we get the natural logarithm of the absolute value of y is equal to x squared, and then we have to have a constant of integration, and we can make one constant of integration. And whenever we do this, we can also write this a different way. If this side is equal to this side, then e raised to this side is equal to e raised to this side. So what we will get is the absolute value of y, which is e to the ln absolute y, is equal to e raised to the x squared plus c1. But e to the x squared plus c1 in the exponent is the same thing as e to the x squared times e to the c1. So y is equal to that. And so the solution, and we could just say that e to the c1 is a constant, and so we could say that this is the general solution. Now we can check to see that is by taking the derivative and substituting in and see if it works, and we see that it does. Both sides end up being the same thing, and that means the statement is true. All right, here in example 4 then, we're to find a particular solution of this differential equation. And it's a particular solution because we have an initial condition which allows us to find what the constant is. So first, what we're going to do is we're going to algebraically separate the variables. So what we can do is we can add minus x to both sides. And then we can multiply both sides by dx. Now we have 3y squared dy is equal to minus x dx. These are just y's, these are just x's, so this is a separable differential equation, and we've separated the variables. So we can integrate both sides. Now here we add 1 to the exponent and divide by the new exponent, we get y cubed. Here we add 1 to the exponent, divide by the new exponent, and we get minus x squared over 2 plus c, and you see we have an arbitrary constant here. Now what we can do is we can substitute our initial condition. So when we put x to be equal to 0, y is equal to 5. So we put y to be 5 and x to be 0, and we find that c is 125. And then we can even solve this by taking, so the constant is 125, but we can take the cube root, and we can find that y is equal to the cube root of 125 minus x squared over 2. Make sure you can do these kind of problems. Here's another problem. This is not a particular solution. We're going to find a general solution. So we want to solve y prime equal x minus x times y. Now we factor the x out of here. Well, first of all, we'll write this using Leibniz notation. dy dx is equal to x minus xy. And then we're going to factor the x out of here and multiply both sides by dx. Now if we divide both sides by the factor 1 minus y, we get dy over 1 minus y is equal to x dx. And again, you can't have y to be equal to 1 because you'll be dividing by 0. So that's an important constraint. So now we have a separable differential equation. We have y's here, we have x's here, so we can integrate both sides. We integrate this right-hand side, we add 1 to the exponent, divide by the new exponent, and we put our constant over here. On the other side, when we integrate, we have to change variables because the u is 1 minus y, so we get negative the natural logarithm of 1 minus y. So that is what we have here. And going from this step to this step, we multiply all the way through by the negative 1 to get all the negatives on this side. And then we exponentiate both sides. So we take this side is equal to this side, so e raised to this side is equal to e raised to this side. Now, as we did before, e to the ln, absolute 1 minus y is just 1 minus y. And on the other side, this is e raised to that exponent. And if we recognize again that e to the minus c1 could be called c2, what we get is this expression. We're putting a plus and minus here. And so then we'll solve for y, and we get y is equal to this. Now, minus C2 could be called capital C, and so the general solution could be written this way, where C does not equal to 0. And the reason C can't be 0 is because y can't be 1. Let's solve a problem, and this is recall from section 2.4 when we studied this. This was the uninhibited growth model, and we're going to use that to solve a business problem. Now, the constant proportionality K is called the continuous growth rate. You might remember that from the earlier chapter. So here we're looking at a business problem where we're talking about a growth of a savings account. So you have a person named Daryl invests $1,000 in an account that earns interest at a rate of 4.5%, compounded continuously. We find the particular solution of the differential equation that describes the growth in the value of this account. Well, we know that if A of t is the amount in dollars, then because of continuous compounding, we know that the derivative of A with respect to t is k times A. And this is a separable equation because I can multiply both sides by t and divide by A, and I get this. So this is a separable equation. We have just t's on this side, we have just a's on this side. So we integrate both sides, we get the natural logarithm of A is positive here, is equal to kt plus c. This is where we put the constant. Now, since this side is equal to this side, we can take e to the this side to get A, and e to the this is equal to this, and then we can use the property here of exponents again, so that is e to the c times e to the kt. And we can say that, e to the c, we're just going to call it as a constant this. Now, we knew in this problem that the interest rate was 4.5%, and that means k, the continuous growth rate, is this. And since a to the 0 is equal to 1,000, we can solve for c, and c is 1,000. That means that the particular solution is a of t is equal to 1,000 e to the 0.045t, and you could graph this and you would have an expression for the growth of the savings account over time. Here's an application to economics, and it calls us to think about the elasticity that we studied before. So suppose the elasticity of demand for a certain product, and that was studied in chapter 3.7, is 1 for all x greater than 0. Find the demand function, Q equal d of x. Well, we recall the definition of the elasticity of demand is given by E of x is equal to minus x d prime of x over d. But this is equal to 1, so we'll substitute 1 for E of x, and we have this. Now, this ends up being a separable differential equation. And in fact, writing this another way, we could say that when we call Q is equal to d of t, then we got a d of t in the denominator, so there's the q, and this is d prime, which is dq dx. So we could write it this way. Now we will separate variables. We'll divide both sides by x. Actually, we'll divide both sides by x and multiply both sides by dx, and we will get this expression. So you see the left-hand side is just a function of x, the right-hand side is a function only of q. So we integrate both sides, we get that the ln of x is equal to the negative of the ln of q plus c1. So we can raise both sides. This side is equal to this side, so I can take e to this side. And I will, actually before I do that, I move this over. So this is the natural logarithm of the product. And so then we take the exponential of both sides, and we end up with x times q, which is what e to the ln xq is equal to a constant. So that means q is c over x, or the demand function is c over x. And this result is characteristic of anything where the elasticity is always 1. Here's an application to psychology. In psychology, One model of stimulus and response asserts that the rate of change of the response to the stimulus, dr ds, of a reaction with respect to a stimulus is inversely proportional to the intensity of the stimulus. That is, dr ds is equal to k over s, where k is a positive constant. And this is known as the Weber-Fechner law. To solve this, then, what we're going to do is we're going to multiply both sides by ds, and then we have dr is equal to k. This is ds over s. We'll integrate both sides. When you integrate dr, you get r is equal to k. This is the natural logarithm of s plus c. Now, if we let S0 be the lowest level of a stimulus that can be detected, this is called the threshold value or detection value. And so we're going to say that R of S0 is equal to 0 because that's the lowest one you can detect. So if we substitute that in, we figure out what this constant is. So if we replace C in the equation that we have here for 5 with this, which we found out was the constant, we'll get this R is equal to k, the natural logarithm of s, minus k ln of s0. But this is, factor out the k, this is the difference of the logarithms, which is the logarithm of a quotient. So R is equal to k ln of s over s0. Now this is the solution of the original differential equation. Now if you look at the graphs of dr ds and r, then you'll see that r grows like this and dr ds goes like this. So the stimulus and response get larger, the rate of change decreases. And so that means, for example, if a light has a 6-watt bulb in it, if the bulb were suddenly changed to an 8-watt bulb, you would probably be very aware of the difference. That is, your response would be strong. If the bulb were changed from a 10 to a 12, your response would increase, but not as dramatically as it did going from 6 to 8. A change from a 12 to 14-watt bulb will be even less increase in your response, and so on. This table lists some other detection thresholds that you might find interesting. The tick of a watch 20 feet away in a quiet room is the threshold of hearing. Taste is water diluted in sugar with a ratio of 1 teaspoon to 2 gallons. Smell, 1 drop of perfume diluted into a volume of 3 average-sized rooms. Perfume is very strong, you might notice here. And by the way, your sense of sound is also very strong. And touch. The wing of a bee dropped on your neck at a distance of 1 centimeter, about 1/8 of an inch. So again, your sense of touch is very strong. Just to summarize then, we talked about differential equations. We talked about general solutions of differential equations. We talked about solving initial value problems where we found particular solutions. We talked again about the uninhibited growth model. We talked about identifying and solving separable differential equations and how to solve separable differential equations. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.